One thing you'll see in this chapter is that there's something the text will refer to as the division algorithm, which is really the algebraic version of this relationship I just showed you here. That when we are working with polynomials, we can have expressions that are in the variable x, but our dividend f of x is still the divisor times the quotient plus the remainder. Now, one important consideration is that if the remainder is 0, then f of x can be written as just the product of these two factors. The remainder term is gone, and so this will be important when we look at the factor theorem at the end of the chapter and solve for roots of polynomials. We can express a polynomial f of x as the product of two factors and then use those factors to solve for roots of the function. When we do polynomial long division, there's two things you have to do with the dividend when you set up the long division. One, the powers of the variable must be in this descending order when we set up the long division. And if there are any missing powers of the variable, we have to use coefficient of 0 placeholders when we do the division. And I'll show you examples of this. In example 1 on page 383 of your textbook, they give us this problem. Divide x squared plus 10x plus 21 divided by x plus 3. And I've put it into our traditional long division form. This is the divisor, and this is our dividend. And notice we have the descending powers of the variable. This is the square, the first power, and this is really to the 0 power, or the constant. Now, how do you get started? Well, we always want to look at this first term here. And you can either take this term and divide it by this term in the divisor, or one way I like to look at it is, well, what times this value here will match this leading term? So what times x gives me x squared? That is x. Now, when you determine this value, you have to make sure that the same powers of the variable are lined up. So notice, this is x to the first power. It has to be lined up over the x to the first power term in the dividend, not over the x squared and not over the constant. It needs to be right here. And then we multiply. X times x plus 3 is x squared plus 3x. And then we're going to subtract. Now this is where you want to be careful. And the text won't show you this, but I will. Right? I recommend you add parentheses. Because when you subtract, by design, these first two terms should always cancel out. However, unlike our arithmetic long division, where we really just have one number subtracted from another, which is simpler, in polynomial long division, notice there's the second term. And this negative has to be distributed across that term. So what we really have here is 10x minus 3x, which is then 7x. So be careful with that second term. Then I'll bring down the next term. And now I want to match this leading term. What times x would give me 7? Well, that'd be plus 7. And so 7 times x plus 3, that'll be 7x plus 21. I'll subtract. And notice we get a remainder of 0. And this is going to speak to the factor theorem. When we have a remainder of 0, it means that we can take our dividend, f of x, and express it as the product of two factors, the dividend and the quotient. And notice if I had just said, hey, set this problem equal to 0 and solve, if we were doing something like that, then of course you'd say the roots are x equals minus 3 and minus 7. So that's going to connect with what we're going to do with the factor theorem at the end of the chapter. In example 3 on page 386, they give us this problem. 6x to the fourth plus 5x cubed plus 3x minus 5 divided by 3x squared minus 2x. Now this is an example where you have to use a coefficient of 0 placeholder for a missing power of the variable. So notice the squared term is missing. So when we set up the dividend, right, we have our powers in descending order, but because we're missing the x squared term, I have to put it in here with a coefficient of 0 as we work the problem. So now, let's do our division. What times 3x squared would give me 6x to the fourth? Well, that would be 2x squared, and again, I have to line it up over the x squared term. So then we multiply. This would be 6x to the fourth minus 4x cubed. Again, I'm going to add my parentheses to subtract. By design, these terms should cancel. And now minus times a minus is a plus. So 5 plus 4, that will be 9x cubed. And even though that has a 0 coefficient, we do bring that x squared term down. Now, what times 3x squared gives me 9x cubed? Well, that would be 3x. So 3x times 3x squared is 9x cubed. 3x times minus 2x minus 6x squared. Again, I'll add my parentheses and subtract. And minus a minus becomes a plus 6. And 0 plus 6x squared is 6x squared. And I'll bring down the next term, 3x. Now let's match this leading term 6x squared. What times 3x squared gives me 6x squared? Well, that will be plus 2. So again, we'll multiply. This will be 6x squared minus 4x. We'll subtract. And by design, these will cancel. And now we have a 3 plus 4 will be a 7x. And then we bring down the last term, 7x minus 5. And so remember, when you write the answer, we'll have the quotient, and any remainder will be written over the divisor. And so there is your final answer. Now, do pencil problem number 1. Now let's look at the last topic in section 3.3, which is the factor theorem. And this is going to look at examples where the divisor is of a form x minus c. Now, if we revisit the division algorithm, f of x would equal our divisor x minus c times the quotient q of x and plus some constant remainder, r. Now, there is something called the remainder theorem, where the remainder in your division would be the function evaluated at some value c. But if that value, f of c, equals 0, then this term r drops away. And so our dividend, f of x, will just be the product of the divisor x minus c times the quotient. And notice, if you look, that means that our dividend is really in a factored form with this one factor, then times the quotient. So if f of c, or your remainder, is 0, then that means x minus c is a factor of f of x. Conversely, we can look at the factor theorem in the reverse direction. If x minus c is a factor of f of x, well, with this division algorithm, well, evaluate f at the value of c. Well, if we substitute c here into this expression, well, c minus c times q of x, c minus c is 0, so 0 times q of x is 0. So to summarize, if the function at a particular value c is equal to 0, then x minus c must be a factor of f of x. And if x minus c is a factor of f of x, then the function evaluated at that value of c equals 0 as well. Let's revisit example 1 to put some concrete numbers to this theorem. So our dividend was x squared plus 10x plus 21. Our divisor was x plus 3. And we got a division with 0 remainder, which was x plus 7 for the quotient. So, because there's no remainder, we could express our dividend, f of x, as the product of the divisor times the quotient. And if we were to solve for this equation, or the roots of the equation when we set f of x equal to 0, well, in factored form, the roots are clearly minus 3 and minus 7. And those are the values for which f of x would equal 0, right? So f of c in this case, whether it be minus 3 or minus 7, would both be 0. So, again, in this problem, if f of minus 3 is 0, well, that means x minus minus 3, or x plus 3, must be a factor. And if x plus 3 is a factor, well, that must mean that f of minus 3 is 0. Let's look at example 6 on page 391 of the textbook. So, solve 2x cubed minus 3x squared minus 11x plus 6 equals 0, given 3 is a 0 of f of x. So that fact is really important to get the problem started. What they're saying is that f of 3 is equal to 0. So by the factor theorem, that means if this value c is 3, then our factor x minus c, and in this case x minus 3, is a factor of f of x. So to solve the polynomial for its other roots, we want to divide it by x minus 3. So now that we've set up the long division, let's do it. So what times x gives me 2x cubed? That would be 2x squared. And we'll multiply. This is 2x cubed minus 6x squared. We'll subtract. These will cancel. We'll get a minus 3x squared plus 6x squared is a positive 3x squared. Bring down the 11x. What times x gives me 3x squared? That's a plus 3x. We'll get 3x squared minus 9x. Again, I'll subtract. These will cancel by design. Minus 11 plus 9x is a minus 2x. And then we get plus 6. What times x gives me minus 2x? That would be minus 2. We'll get minus 2x plus 6. We'll subtract. And in this case, we will get a 0 remainder. And that's important because now what it means is that we can take our dividend, f of x is 2x cubed minus 3x squared minus 11x plus 6, and write it as a product of factors. One being the divisor, x minus 3, the other being the quotient. Now, what makes these factors 0? Well, this is the original 0 they gave us, correct? When x is 3, this factor is clearly 0. That's one of the roots. But now what we need to do is solve this quadratic equation to find the other two roots. Now remember, with our quadratic equations, you always want to try to factor it first if you can. And in this case, we can factor this, right? There's really only one way to get 2x squared. That's 2x times x. And there's really only one way to get 2. That's 1 times 2. And eventually we can figure out that this would have to be minus 1 and plus 2. That equals 0. And so what are our factors? Or roots, excuse me, from the factors? Well, we'll get x equals 3, 1/2, and minus 2. And just note, in solution set notation, the roots are written in ascending order. And so those are the three roots or solutions that make this function f of x equal to 0. So when finding solutions of a polynomial using the factor theorem, whenever you're given a root, whether it's just stated in the problem or being given an x-intercept off the graph, which is also a root of the function, whatever that value of c is, divide your polynomial by the factor x minus c and look for getting a remainder of 0. If you do, that means you have found a factor and a root of the polynomial, and then we can express the dividend as a product of that factor and the quotient from the division and solve for all the remaining roots. Now, do pencil problem 4.